So thanks to the organizers for putting together this workshop and the conference, which has been a lot of fun. So it's also great that they've invited me to come here to give a talk. I was a postdoc here a few years back and had a wonderful time, formative years of my life. So it's wonderful to be back. All right, so the work that I'm going to talk about was done with Ji-Hwan Dong, who till recently was a graduate student at MIT. He's on his way to Berkeley, the postdoc, and Adarsh Patri, who's a postdoc at MIT. And most of the talk will be on a paper that just appeared yesterday. Okay, so this work on rhombohedral pentalayer graphene has been mentioned several times during this conference. We also heard from Long. This Long Ju, in case you don't recognize him. And it's been absolutely wonderful for me to have Long as my colleague, learn lots of things, lots of beautiful things. So the system is this, I'm going to be I'll go through the introduction very quickly because we've heard so many talks on this system and the theory of this system, the basic theory of this system. So it's 5 layers of graphene stacked in this rhombohedral pattern, dual gated samples, and it's aligned with boron nitride on hexagonal boron nitride on one side, nearly aligned, and that produces the Moiré pattern. And there's a large displacement field that drives conduction electrons away from the Moiré, right? So the phase diagram is a function of displacement field and density is something that you saw in many talks. So there is an integer quantum anomalous Hall state at filling 1 of the Moiré lattice. And as you go down, in this first experiment, they saw a sequence of fractional quantum anomalous Hall states. There's the data on the integer state. You see nice hysteresis and quantization and so on and so forth. Okay? So the physics of this 5-layer rhombohedral graphene or n-layer rhombohedral graphene generally. So the pristine 5-layer system, for instance, in the absence of Moiré, has a nearly flat dispersion with some Berry curvature. These various dispersions are with various displacement fields. So for instance, if you look here, there's a nearly flat portion, and there's a large Berry curvature somewhere within some radius of 0 momentum. And there's strong Coulomb interactions, and there's a weak Moiré potential because the displacement field has driven the conduction electrons away from where the Moiré acts. Okay, so I'm just going to spend one slide, or half a slide really, on this topic of what's going on at nu equals 1 that has been discussed by many speakers throughout this meeting. So the lightning summary of what we've learned is that the key idea to understand this nu equals 1 state is that it's not a Chern insulator in the same sense that, say, twisted MOT2 or something is a Chern insulator, or TBLG aligned with HBN. Rather, you need electron-electron interactions to not just flavor polarize, but even produce the incompressible many-body state, which has an integer quantum Hall effect, right? So as we heard from many people, there's a bunch of papers that showed last year that within Hartree-Fock that this phenomenon happens. There's a simple explanation of the Hartree-Fock results, both from our work and the work that you just heard from Dan Parker. And several other people who were at this meeting, Shankar and Andre, who's around, have worked on this since. And the story for nu equals 1 is broadly consistent across anybody who studied this problem in the last 1 year. Right? That it's an interaction-induced Chern insulator is, I think, pretty clear at this stage. So the interpretation of this is a bit more delicate. That it's, as we've heard multiple times, this is, it's good to view this as an anomalous Hall crystal, possibly encouraged by the presence of a weak Moiré potential. So this state breaks time reversal spontaneously and it breaks continuum translation spontaneously, though in the real system, continuum translation is an approximate but not exact symmetry, right? And it has a non-zero Chern number for the occupied Hartree-Fock bands. Okay, so that's all I'm going to say about the state. Everything else that I could say about it has already been said. Right? There's no point in repeating story. So let's ask about, Hartree-Fock is Hartree-Fock, right? We should do it, but then we should move on. And so let's ask about, first of all, in this problem, it's very hard to move on. But let's think about what we might expect, right? Now, the precise phase diagram, beyond Hartree-Fock should be determined by very difficult many-body calculations, which beyond the capability of what we currently know how to do, right? Or you could look to experiments to get some idea of what the real phase diagram is. But let's see what we can expect, right? So we expect that as you tune the ratio of Coulomb to kinetic energies, that if the Coulomb energy dominates, that maybe the Hartree-Fock story is right, and you get this anomalous Hall crystal. This is in the absence of the Moiré. And if the kinetic energy dominates, that you get a Fermi liquid, and Hartree-Fock gives you some, gives you this Hall crystal solution over a wide range of this ratio. Right? Now, from experience with Wigner crystallization and the 2D electron gas or the 3D electron gas, you might expect that Hartree-Fock overestimates the stability of the crystal compared to the liquid. Right? So, in general, we should expect that the true transition occurs at a much larger value of this parameter, right, than what you might naively expect based on Hartree-Fock. So in this intermediate regime, where Hartree-Fock would have given you this Hall crystal, what you might actually get is just a correlated Fermi liquid. That's what happens in the standard problem of the 2D electron gas. And the transition is, the true transition would be a first order transition. Okay. Now the interesting thing is to ask what happens to this expected story if you turn on a Moiré potential, right? That matches whose unit cell fits the density, just matches the density. Now, again, experience with ordinary correlated electrons tells us that quite likely the correlated Fermi liquid and the crystal state, that their energies are going to be very, very similar, right?
Senthil, this is a semantic question. What is the precise definition of correlated Fermi liquids? Is copper a correlated Fermi liquid?
Sure. Copper is a correlated Fermi liquid. It's not a strongly correlated Fermi liquid, but
there is some interaction.
Yeah, so RS is 5 or 6, that's correlated, right? In the 2D electron gas, if RS is 10, that's certainly strongly correlated, right? There'd be a mass renormalization, the quasi-particle weight will be small. The quasi-particle weight is a good measure of how correlated you are. If it's much smaller than 1, then you're strongly correlated. So, if these two states, since the energy is determined by short distance physics, they probably have very similar energies. That's routinely seen in all kinds of strong correlation problems. So, so then when you turn on this periodic potential, any crystal will gain energy to linear order in the strength of the periodic potential. It will gain commensuration energy, while the Fermi liquid will only gain energy at quadratic order. So, so what you expect is that the phase boundary curves this way, right? Now, again, we don't know what really happens in this problem, but in the usual Gilliam problem, 2D electron gas, the energy difference between the Fermi liquid and the crystal is 1 part in 10 to the 3 energy difference per particle, all the way down to RS of, much less than 10, even though the crystallization occurs at an RS of 35 or something like that. Right? So deep into the space, the crystal is almost the ground state, but ultimately it's not. It's the liquid. Right? So what that means is that an unnaturally weak Moiré potential can tip the balance between these two closely competing states and stabilize the crystal, even though in the absence of this periodic potential, the true ground state is just the liquid. Right? So I think this is important to keep in mind. So we call this a Moiré-enabled Hall crystal. In this context, it will be a Hall crystal. It's Moiré-enabled because you need the Moiré to push you into the state. But once it's there, its gap will be determined by Coulomb interactions and so on and so forth. So in that sense, the Hartree-Fock is sort of okay, even here, so long as you have a tiny Moiré potential. Right? Now, I don't know, so there's some expectation, and we don't know where the real system will fall, but the presence of even a tiny Moiré potential is an advantage for stabilizing the Hall crystal, and it vastly expands the range of parameters where you might expect to get this interaction-induced churnings later. Right? Yeah?
So this DM will have also be disorder?
Disorder? Oh yeah, sure. But, I'm not going to think about disorder at this stage. Or rather, we have expectations for what disorder will do, but this is not the right forum or context to worry about that during this talk. I can talk to you separately. I can tell you what we understand, what we think will happen. Okay. So, there's a theoretical physics institute, so let's try to do theory, in a pure sense. Let's just try to think about what might happen if so we have a story for what happens at nu equals 1. It's an interaction-induced Chern insulator, which we would like to interpret, which we interpret as this anomalous Hall crystal, possibly enabled by the Moiré, or at the very least, certainly pinned by Moiré, right? But then what happens once you go to lower dopings, right, to lower fillings? Now, you can answer the question within Hartree-Fock with the negligible Moiré potential, and indeed, you find that in a range of density, the anomalous Hall crystal will survive, and the crystal period will of course be set by the electron density if you don't have any Moiré. It's just going to be determined by the interparticle spacing. And I'll denote this crystal AHC rho. The subscript rho means the crystal period is set by the electron density. So let's think about what might happen in real life with Hartree-Fock as some loose guidance. Right? So some possibilities are listed here. First, you might imagine a possibility where this AHC rho state survives even with the real Moiré potential and even beyond Hartree-Fock. That's just a candidate state that you could contemplate. Okay? Now, there are other things you could contemplate, that this AHC rho crystal, which exists in the absence of Moiré, that when you turn on the Moiré, which now has a different period compared to the AHC rho's lattice spacing, that this crystal distorts to gain commensuration energy, right? Or rather, distorts this way to gain commensuration energy. But then that will put the crystal at the wrong density. So then you need to have some number of holes that are introduced into the system, or vacancies if you think in terms of crystals. Right? So so there's another possibility that the AHC rho distorts to lock to the Moiré. And I'll call that resulting state AHC M. M is for Moiré. So it's changed its period. It's the period that it would naturally have had. The external periodic potential has forced some distortion, and that is an integer Chern insulator. But then on top of that, because of the charge density that we put the system at, we need to have some holes, and those holes will form some many-body state. There are many things that the holes can do. They can crystallize, and they can form their own crystal, right? So you have this AHCM that's locked to the Moiré, and then you have some density of holes that have formed the crystal themselves. Or the holes can form a fractional quantum Hall state at special fillings. Or the holes can just form a Fermi liquid, right? You can get a metal. And finally, at low density, certainly, the holes can just be localized, Anderson localized because of disorder, right? So all of these are possible. Now, so microscopic theory So I said let's do pure theory for a reason, because soon, I think it's clear to me at least, and probably to many people in this room, that it's almost impossible at this instant of time to be a pure theorist in this problem, right? Uh, you know, microscopic theory is extremely hard. If you don't want to do Hartley Fock or don't want to do something else that we don't know how much we can trust, so many of these states will have ground state energies that are very close to each other, very typical of strong correlation problems. They have many competing states with very small energy differences, right? I mean, Dan Parker was voicing similar opinions, I think. And you know, and a consequence of that is that if you have small changes of parameters, you can completely change the ground state, right? And reliable theoretical calculation of ground state energies is tough in this situation. We've known that for a long time in other problems, and it's probably even tougher here. And it's not really possible with existing tools, right? So we have to stop being pure theorists. The best strategy we have for progress is to look to experiments, right? Which is, I think, a good thing for our field. There are fields in which that is not an option, right? But for us, that's a great thing, and we should embrace it. So that's what I'm going to do. Let's look to experiments and see what we learn, right? So what about fillings half less than nu less than 1? Let me focus on that range. So there are a lot of the interesting things are going on. Now, so this is the phase diagram that Long told us in his original paper. You have the nu equals 1 state here, this the integer quantum Hall state, and you dope, and you see all kinds of things. You see a metal here. So clearly you can form a metal, that's allowed, and it happens in the phase diagram. But as you dope, as you go along this strip, the most interesting thing that happens, as you've heard many times by now, is all these fractional quantum anomalous Hall states, or fractional Chern insulators, right? Okay, so this was the story in 2023, and in 2024 things have gotten refined a bit, and Jed was asking a question, so I'm going to address that. So Long showed us earlier this week about his new data, where you go to lower temperature than here. Here the electron temperature was, he now thinks, was about 200 to 300 millikelvin, but now you go to even lower temperature and lower the current at which you do the transport measurements. So then the phase diagram changes, right? And the same phase diagram evolves to something like this, where you see these blue regions, this tiny blue region here, big blue region, tiny blue region. So this region is what Long calls an extended integer quantum anomalous Hall effect, and that dominates the phase diagram in the region where previously the most interesting thing was where the fractional quantum Hall states. So now you see this thing dominating. It dominates, but the Jane states are also seen. It's not that the Jane states are gone. Some of the Jane states are also seen in the same phase diagram, right? And the Jane states will make a reappearance, they make a reappearance when Long does various kinds of things, perturbations to this phase diagram. Okay, so that's the new story. So again, so let me show a little bit more data, and I'll talk about the experiment a bit more. So Long talked about it on Tuesday, and a somewhat similar data from Matt Jankovich, who's somewhere in the room, there he is, that he'll talk about on Friday. Yeah, so what I showed earlier was the RxX plot. There's also an RxY plot. And in this region, you can't quite see it in this color plot, but this color corresponds to Rxy of h over e squared. So that's why it's called an integer quantum Hall state, an extended integer quantum Hall state. Someone was asking me why it's called extended. It's extended because it extends in a range of density. Right? That's the terminology. So if you look at the line cut here on this dashed line and look at Rxx at the lowest temperatures, you see that you have this integer state where Rxx is 0, and then it does something, and then it goes back to 0 over a wide range. Likewise, Rxy is quantized to be an integer, and then it's to 1, and then it stays quantized to be 1 over this wide range, which covers a huge range of densities. Okay?
When the remain are still decreasing in temperature.
Sorry?
You said some sequences remain. Are they still decreasing with T? Or?
I think the gaps there may be very small, so there may not be enough temperature range, but if Long is in the room, he can clarify.
The gap of what?
Of the higher Jane states, which survive in the phase diagram at lower T, right? To see what happens if you go to even lower T, I mean, it's already down at, very, very low temperature. So, these are some of the things that I want to think about, and so let me present some of the salient phenomena that are reported in the experimental paper. So this extended integer anomalous quantum Hall effect is seen at low temperature and low current in a wide range of fillings. That's what I just showed. Now, there's something remarkable that happens. At low temperature, so you stick to the lowest temperature at which you can do the measurements, and you increase the current at which you do the measurements, right? You're sitting at low temperature and increasing the current, and then you get different things that go on depending on the filling. If your filling is at some generic filling, one thing happens, and if you're at the Jane filling, something else happens. So let me first tell you what happens at a generic filling. The generic filling, you transition to a metal, okay? And this metal, so this is the differential resistance, or XX, plotted as a function of the DC current. And it has this curve, this characteristic shape that Long showed in his talk. So it's 0 here, and there's a peak, and then it retreats to a finite value at higher currents, right? So Long said this in his talk and in his paper, these IV curves resemble a superconductor. But of course, we don't have a superconductor here, right? So that's one of the things we want to understand. So it's an unusual structure in that there's a peak in the differential resistance at a threshold current, right? And then it goes into a metal, right? It starts from this integer quantum Hall state, has a peak in the resistance, in the differential resistance, and then goes to the metal. Now, that's what happens at generic fillings. If you sit at the Jane fillings, P over 2P plus 1, between fillings half and 1, then there's a current-driven transition between this extended quantum anomalous Hall effect and the fractional quantum anomalous Hall effect, right? At the lowest temperature. So the current-induced transition from integer to fraction. Which again is remarkable. So you see that here as a function of current. As the color increases, you increase the current. So the lowest currents, you have an integer state. As you increase the current at 2/3, you get 2/3, 3 over 2, h over e squared, 3/5, you get 5 over 3, and so on and so forth. Okay? Now finally, if you keep your current low, or you could keep it somewhat higher, I guess, but you increase temperature, you evolve from the extended quantum anomalous Hall state to the fractional quantum anomalous Hall state. And that's seen here. As you increase the temperature, you go from this data to this data, right? Now, there's a remarkable fact about this transition that I think is very, very important, and that is that the critical current, so the summary is that at low temperature, you can move out of the extended quantum anomalous Hall state by increasing the electric current. So there's a critical current for this phase, and this critical current has dips at all the Jane fillings, right? So it has local minima at the Jane fillings. Okay, I'll come back to this later, but I think this has some important information. Okay, so now let's go back to our theory guesses and see what amongst the naive guesses we had are there states that can fit the bill, right? So this first candidate that I talked about, this AHC rho, which somehow has survived beyond Hartley Fock and beyond no Moiré, No, that in the presence of some impurities will be a pinned state, and that will have an integer quantum Hall effect at any density. Right? So that's a candidate. Amongst these states, where you're doping holes into the nu equals 1 state, if the holes crystallize, then again the impurities or something else will pin that crystal, and you'll again get an integer quantum Hall state. Of course, we're not seeing a fractional quantum Hall state, so it's not this, and it's not a Fermi liquid either. Really? Okay. All right. So there are two crystalline states at fractional filling that we could be thinking about as possible candidates for this extended integer quantum anomalous Hall effect. So both of these break the Moiré translation symmetry, and so I'll call them EIQAH crystals, and they'll be pinned by impurities or at special fillings by commensuration with Moiré. Right? So the questions that we want to ask are, what's the nature of the crystalline ordering? What about these current-driven deepening transitions? What about the competition with the Jane fractional quantum Hall state? And what about microscopics? Right? So I have nothing to say about microscopics today. I'll try to address the others to some extent. It does, but I don't want to talk about that either. Have 5 minutes. We can talk about that at some later stage. Okay, so let me start with this, or maybe I'll only be able to talk about this given the time. Let me talk about the integer quantum Hall plus whole crystal and think about its properties. Right? Try to think about it in some general way. So the holes, when you dope holes into the nu equals 1 state, they'll feel not just the bare Moiré potential, but they'll feel an enhanced Moiré potential because there's already a nu equals 1 anomalous Hall crystal that is locked to the Moiré. Right? That will generate an extra potential that the holes see. So the charge ordering pattern will be complicated because there's an interplay of Coulomb and the effective Moiré potential, not the bare Moiré potential, but the effective one. You might have to take that lattice into account. Now, the presence of the effective Moiré potential means that you might have stronger pinning at commensurate fillings. At generic fillings, only impurities can pin this crystal. It will be incommensurate with the Moiré lattice. But at commensurate fillings, like for instance, if the whole filling is 1/3, you can have this structure, which nicely fits the Moiré superlattice, and then it will just get pinned very strongly. Okay, so let me talk about the depinning transition, because that may be one of the most interesting phenomena. So let's ask about the effect of a current, let's say that I run along, say, the x-axis, or the whole crystal at generic fillings, not at the special commensurate fillings. And then the whole crystal is pinned by impurities, and we can ask what happens. So at low current, only the integer quantum Hall component will carry the current. When I run a current, only the integer quantum Hall, the nu equals 1 component, will transport the current, and that will lead to a Hall voltage, which is the familiar one. Okay? The Hall voltage, the electric field is along the y direction. Now the crystal, this incommensurate Hall crystal, will feel this y direction electric field, and eventually, as I increase the current, this electric field will increase, and at low currents, it'll stay pinned, but eventually there'll be a threshold, and it'll start sliding in the y direction. Running a current in the x direction, and beyond critical current, it'll start sliding in the y direction. Right? But in the y direction, I have no current. Right? My current is, the system is biased to have a current in the x direction. So there will be something that cancels the current produced by the sliding crystal. And that again can only be this integer quantum Hall component. So the integer quantum Hall must develop a current in the opposite direction that is exactly cancels this y direction current. Right? But this integer quantum Hall current that develops in this direction will then lead to a Hall voltage in the x direction. Right? So then I'll get a resistance in the direction of the current flow, a longitudinal resistance. Okay? So the longitudinal voltage, the voltage along the x direction is, h over e squared times the y component of the integer quantum Hall current, which is exactly the same up to sign as the y component of the CDW current, right? Evaluated at a voltage which is given by HOE squared times Ix, right? So we can take a derivative of this equation to get the differential longitudinal resistance. We find a nice equation that says that this differential resistance is proportional to the differential conductivity of the sliding Hall crystal, right? So that's a key result. And can I do a Bernewig and take 3 more slides? Andrea will forgive me, I think. So we need to understand what happens when to this deepening crystal, right? This crystal that's spinned by impurities and then it's deepened by an electric field, because we need to know what the differential conductance of a sliding crystal does. Okay? So this is an old problem in StatMech, studied for 40, 50 years. Very difficult problem. What's known is that there's a sharp zero temperature dynamical phase transition, a second order dynamical phase transition at a threshold electric field. And there's different behavior depending on whether the sliding is elastic.
Senthil, it is completely classical.
It's completely classical, absolutely. Yeah, it's complete. There's an old story. It's classical, but you know, whether the sliding is elastic or whether the sliding is plastic. Plastic means you introduce topological defects. Maybe it's a part of the crystal gets stuck to some impurities, and the other part moves, so you tear the crystal apart. Blah blah blah. So at weak disorder, people expect that it will be elastic, and in the elastic regime, there's numerical calculations that show that the CDW current as functional electric field has this shape. Okay, so you can take a derivative of this curve to get the differential conductance, and because it curves this way, the derivative, the differential conductance will have a peak, right? A divergent peak, and that's indeed what you get. Now in our problem, this differential conductance actually gives us the measured differential resistance, right? So then the differential resistance will have this peak, and then it will die off. Right? So that, I think, is a possible origin of this IV curve that Long says looks like a superconductor. Right? There's a peak in the differential longitudinal resistance and not in the conductance. And it comes from a very simple combination of the sliding CDW physics and the presence of an integer quantum Hall component. Okay. I should finish. Let me just make one remark about what happens to the Jane fillings, and then I'll stop. So at the Jane fillings, you have, the competition that determines the physics is that between this Hall crystal state and the fractional quantum anomalous Hall state, right? Now in the whole picture, you can regard this fractional quantum anomalous Hall state as an integer quantum Hall state plus a Jane state of holes. So the competition really is between a crystal of holes and a Jane state of holes, right? And we expect that they are very close in energy. In studies of fractional quantum Hall, people know that crystal and quantum Hall states are very close in energy. So the evolution with some tuning parameter, like displacement field, we expect that both states can be stable in some range of parameters, with the simplest possibility is that there's a first order transition, right? And I'll just assume it's first order. So then, with this in mind, let me provide an interpretation of the experiments. So let's recall that this critical current for transitions out of this state has a dip at the Jane filling, right? Now, at the Jane filling is when you might have thought that commensuration effects are strongest, that you can pin the crystal more easily, but that's not what happens, right? And furthermore, the high current state is not a metal, but it's a fractional quantum Hall state. So the proposal that we have is that the current-induced transition at the Jane fillings is not a deepening transition, unlike at generic fillings. Rather, the deepening is preempted by an equilibrium phase transition between the integer and fractional quantum Hall states, right? So how can you be in equilibrium in a current-carrying state? It's allowed if you have a quantum Hall effect, okay? So then, we can study the ground state competition at non-zero current. Non-zero current really means in a quantum Hall system, there's a Hall voltage. It's really studying the competition as function of electric field. And that competition depends on the dielectric polarizability of either quantum Hall state. And we don't really know how to calculate this dielectric polarizability, except if the Jane state has a very high P, then we can argue that since it's very close to the composite from a liquid, which is a compressible state, that the Jane state will have a nearly divergent dielectric polarizability. In fact, increases as mod P, for P becoming very large. So the phase diagram that one gets is something like this, that there's a first order transition at zero current, and then when you turn on a current, this first order phase boundary curves this way, right? At least for large enough P. Now, that's all I know how to do. If someone asks me, will this happen at 2/3? I don't know. It requires serious calculation, which is beyond the purview of this talk. In any case, let me just summarize and say that there's all kinds of interesting things going on in the experiments. And what I discussed is transport and phase transitions of one particular example of this extended quantum anomalous Hall state. They have arguments to say that this is probably the state that's actually pertinent to the experiments, but I don't have time to explain it. And there's a lot of future challenges that will be fun to think about. Let me stop. Yeah, Andrea needs to say something.
I'll take the first question because I have to go home. So in this picture, at the lowest temperatures,
Yeah.
is the system compressible or incompressible at the Jane fillings, and with zero current? And is it compressible or incompressible at the non-Jane?
Right. So at the Jane fillings, it's incompressible.
Even in the whole.
Right. But I mean, at any filling, in the presence of disorder, you have to worry about what,
Let's forget about disorder.
If you forget about disorder, then it's not, it's compressible because it's a crystal, right? You just change the density. If you have disorder, you will pin that, and then it becomes a bit complicated.
But with the Moiré, it's still compressible at U equals 2/3.
I mean, at 2/3, it's not. I mean, at 2/3, because of commensuration, it will lock to the Moiré, right?
Still compressible.
No, once it locks, it's incompressible.
So in thermodynamics, you wouldn't see any difference in compressibility, at least qualitatively, between
The fractional state and the integer state. Yeah, that's it.
You still have peaks at the Jane filling specifically?
In the inverse compressibility. Yeah, that's right. Yeah. Yeah.
Those would now have a different straight slope or the same straight slope?
They should have a different state or so. Yeah.
So Andrea asked a part of my question, but I have many questions for you. All very friendly, Senthil. Don't worry, okay? Very friendly. Okay?
Sure, everything from you is always friendly.
But I would ask two, okay? One is that, the easier one is that, I think this whole looping picture is very nice. It really is very nice, but do you think it's like sensible all the way from nu is equal to 1 to half or below? Because the system, I mean, he sees it everywhere, basically, right? I mean, almost all the way to the strongly insulating phase.
No. So this extended quantum anomalous Hall state is only seen up to nu equals a half. It's not seen below nu equals half.
It's not seen below nu is equal to half yet. But if you look at the data, as I have done for days,
so have
as you lower the temperature, my suspicion, and I'm willing to bet a certain amount of my salary on it, is that it will, it's going in that direction, except for the very strongly insulating phase at very.
Yeah, there's a Wigner crystal at lower density, which is clearly different.
But even at nu is equal to half, that's a half feeling. The whole doping picture.
Right. So again, it's an energetics question, right? It's a question. So the way I presented the story, you start from what happens without Moiré, and maybe I don't know in real life exactly where the phase boundary will be, but there's some anomalous Hall crystal. You turn on the Moiré at some very different period. So question of how much elastic energy are you willing to pay to gain the commensuration
So
energy?
this falls under the hard question.
It's a hard question, so I don't
that's
have
what
the
I
tools
thought.
to answer
I
it.
accept your answer. But my second question is that I must have missed something in your talk because I'm puzzled. You completely ignored the temperature-dependent crossover. To me, that is when I look at the data, that's what I see, you know.
No,
So-
I do have a slide on the temperature-dependent crossover.
But what do you think the story is, according to you? I'm asking you, okay? Because I have my own picture, but I want to know what you think is going on.
I can show you my slide. I think you'll be very happy with my slide.
Oh, make me happy.
So maybe the most important line is the last line.
Oh, I'm happy, okay.
No, the last two lines.
All right,
You know,
you gave the right answer, A+.
No, but let me, one of the other main points about this slide is that the second candidate, which I didn't have time to, whose properties I didn't have time to talk about, AHC rho, within this picture that maybe this first order transition curves to the integer side, within that picture, that candidate is very hard to sustain because that will have a gapless phonon.
Yep.
And so if it's already stable at 0 temperature, it's not going to win against the quantum Hall state, which is the fractional quantum Hall state, which is gapped. Right? So because this state will only increase its entropy and therefore decrease its free energy even more. So this makes this, within this scenario at least, difficult. But then we don't really know how it's going to work for this either, except in the limit of very, very large mod P. Right? Somebody had Patrick had a question. Yeah.
Which I agree with.
No, not in energy. You want the excitations to have very, very low energy. So that they can contribute to entropy. Right?
Right. Okay, but that means you need not just a handful of excitations with that energy. You would need order 1 of those excitations per cell. Like you need an order KB per unit cell.
Yeah, the idea is that you'll thermally excite some finite density of these excitations.
Yeah, but I guess I don't like, and I think we probably agree, but it's not like, if you find like some goldstone with that really low energy, that's not enough, right? Because that's a really small phase space.
Yeah, but the state that we want to win is the fractional quantum Hall state.
Yeah, so that's even worse.
It's worse, right? So, yeah, exactly. So it's a bit of a mystery. So the low temperature current induced transition, I think we have some reasonable understanding of. I don't feel like I understand the finite temperature crossover.
Yeah, why can't you interpret the current as just heating the sample? Just
Yeah,
like the
no, very good. Yeah, people always ask this. So
It's just like the temperature dependent.
yeah, very good. So Long had one answer. I'll give you a different answer as well, but let me first give you Long's answer. So Long's point is that, look, when I change the temperature, everything changes smoothly, monotonically. Well, when I change the current, things change highly non-monotonically. You saw the data, there's a peak in the resistance, and then it comes down. And so these two evolutions look quite different.
I agree completely with Long. They do not look like just a heating.
It doesn't look just, but then I'm a theorist, right? So I can give you a theoretical reason. The state that is starting with at low temperature is this integer quantum Hall state. And you saw the RXX, it's basically 0. Right? So an integer quantum Hall state, a current doesn't produce heat.
In between the two of those states, it's not an integer quantum Hall state.
No, but at low temperature, so long as you're in the integer quantum Hall state and you run a current, that alone is not going to produce heating. It's a dissipationless state. The electric field is perpendicular to the current. Right? Now, of course, in the fractional quantum Hall state, we know that there is RXX as currently measured is not quite 0, but that's the state you're getting into. So where's the initial state unstable, right? So
Also, those gaps were not following the Jane sequence. Is that Any modification in that?
Completely crazy, but this is too soon to worry about gaps. We are worrying about
simpler things. Yeah,
the phase itself.
exactly. Yeah.
Thanks.
My question was actually already asked. It was also related to heating, but I still wonder, can it be that heating happens somewhere else in the sample, say in the contacts, and then this heat propagates?
I don't know. I'll leave it to Long to answer. You know, experimentalists and.
The time scale that you're trying to apply that needs to be considered relative to the temperature scale. I mean, that's heating.
Yeah, there is heating in the contacts and all that. I cannot really answer that. You know. I think what I'm telling you is that there is a theoretical mechanism, right, to where a small current can stabilize a fractional quantum Hall state over an integer quantum Hall state. That's the thing that I can confidently say, at least for some range of P. Now, the experiments also find the stabilization. Maybe they find it because of some other reason. I don't know.
Senthil, thank you for your talk. I'll just ask you to speculate further. In the data, at nu equals 1, there's some extended integer quantum Hall state, but it seems to become weaker as you hold up.
What do you mean by to some extent it's an integer quantum Hall state?
Well, there's extended integer quantum anomalous Hall state, right? Starting around nu equals 1 in the pentadata.
Yes.
You dope holes into it.
Right.
It seems to become weaker,
That's
then
right.
it becomes stronger again.
Yeah.
Do you expect these two to have the same explanation? Do you have some idea why it becomes weaker at intermediate fitting?
I certainly haven't the most trivial idea possible that at very, very low density, you're just localizing the holes. Right? There's a lot of different reasons why the holes would have a large effective mass. You know, they form like polarons or something. And then there's disorder. Right? So this entire crystal picture, when can you talk about a crystal in a disordered system, right? You want the pinning length to be much bigger than the lattice spacing. Now, as you go to lower density, the lattice spacing is increasing at some fixed disorder strength. So eventually, it no longer makes sense to talk about a crystal. You're better off talking about individual particles localized in the random potential. And at very, very low doping, you know, the holes will, when you dope, the holes will locally distort the crystal around them. So they'll form some polaronic object which has a bigger mass. So they'll tend to get localized, right? That's just common sense. So so that region 3 or whatever it was, the very low doping region, the leaking of this integer quantum Hall state into that region is probably just that. And then that physics disappears, and then you have this more collective physics of crystals in this region 2. And then something happens around you, it's half that. There's a tiny region there as well.
Thanks.
Let's take one last question, then we can continue discussion.
Right.
So, Senthil, toward the beginning of your talk, you said that, in your opinion, we should understand the integer quantum anomalous Hall state occurring at nu equals 1 as an interaction-enabled turn insulator, in the sense that we should think about interactions not only as causing flavor polarization, but also creating the churn band,
Right.
in a sense. And I agree that theoretically, we don't have a clear picture microscopically for how the churn band could arise without those effects. But I'm wondering, are there any aspects of the phenomenology that you think establish that point very strongly in that direction? That's the correct picture?
Yeah, so the only thing that I would say is that says the following statement, right? So if you imagine that somehow with some band theory effect, right? This what's called counterfactual thing. So I don't know how seriously you should take it. You know, the gaps presumably would be ridiculously small because the Moiré is not expected to be strong by itself, right? Now, Shankar might know the strength of the gap, but you moved there. But, you know, what we do know is that the integer quantum Hall state, the RxX is really it's really close to 0. It's not like these fractions, this weird residual resistance in the fractions. The integer quantum Hall state is good, right? And it's a pretty robust state. So I can't imagine that the gaps are as tiny as what theoretically you expect of the Moiré potential. But, you know, that particular, second slide of mine that you're asking a question about is what has been the subject of maybe 5 or 6 talks, right? So anyone else, it's a question really to all of us, right? So I think Jumkai wants to give an answer.
There isn't a U=4 gap at the non-proximate side. So, you know, if there is a very large single particle gap, you would expect a U=4 insulator, band insulator.
Well, that's according to whatever microscopic model you're using.
No, I think if I interpret his question correctly, it's like, suppose the world is screwed up on the microscopics completely. Just from experiments, can you convince me that there's an interaction-driven state?
Exactly.
Yeah, that's a good question. I think if people measure the gaps, that might give us some idea. And, you know, if you see these nearly gapless phonon modes or something, you know, that would be, and that would establish this picture even more solidly. Yeah, but, you know, I don't know, is that strong evidence for the kind of question he's asking?
Why not? You guys are band insulators, see a gap, you could do.
No, the band structure depends on chemical potential, and who knows what happens when you insert nu=4.
Okay,
you know,
I still see lots of hands, but one is waiting. So let's thank you and move to the one, please.